All right, welcome to Classic Momentum Problems in 2 dimensions or 2D. I am assuming that you understand how to do momentum problems in 1 dimension. That means only in the x direction or the y direction. If you do not, then I urge you to go to the video before this, which describes classic momentum problems in 1 dimension. If you are in regular junior regular honors physics, you probably don't have to worry about 2 dimensions. If you are in AP 1 or AP Physics C, then you definitely have to worry about 2 dimensions, and this video is for you. This is a very popular 2-dimensional problem that you probably will see in your lectures, in homework, and on the AP test. It's a nice one because it allows you to look at direction more visually and account for momentum in both the x and the y directions, because the ball, which is what this is, just in case it's not looking like it, a ball is coming in and bouncing onto a surface and bouncing off. All right, the floor or the whatever is providing is providing a force that causes it to change direction. All right, so what we are going to do is we are going to ask you to find the change in momentum in the x direction. What is the change in momentum in the y direction? And then draw the vector that shows the overall change in momentum. All right. So if we were to draw the momentum vector of each of these of the balls at beginning, and so this is the initial, and this is the final. Okay. If we were to draw, that would be the direction that the velocity is in, right? So we know that momentum equals mass times velocity, and this is our vector. And since mass doesn't have a direction, the direction of the momentum would be the direction of the velocity. So if we were to and I'm just going to quickly draw this. So this is if this is in the initial case, then, and I'm going to make this a different color. All right. We know that this is theta. So if we were to break up our momentum vector into components, and this is theta, all right, and if this was mv, then this is going to be mv, and it's across or opposite the angle sine of theta, and this one is going to be mv cosine of theta because it's adjacent. Now in the after picture, and let's go back to the blue. If we were to take this, our ball, the momentum is in direction of the velocity. All right, so let's go back to our red again. All right, and so these would be the x and y components, and this is theta. And so now this one is mv cosine theta, and this is mv sine theta. Now, looking at this, I am looking at the directions now and thinking, if I were to plug in numbers, I would have to, well, for this one, it's going up. I would put in a positive value for velocity, and I would put a positive value for velocity here as well. Here, it's going down. So really, if we're not using numbers, then if I'm going to say it in variables, then this is going to be negative mv cosine theta. This is still going in the positive direction, so this will still be positive. Okay, well, if I wanted to find out the change in momentum in the x direction, that is my final x minus the initial x, and so my final my final momentum in the x direction is mv sine of theta minus, and my initial momentum is mv sine of theta. Oh, so this means that there was no change in momentum in the x direction. Well, let's see what it is for the y direction. So this is my final momentum in the y direction minus my initial direction, or initial momentum in the y direction. Remember, change in is always final minus initial. You can get a lot of things wrong if you do initial minus final. So it's final minus initial. So final would be come on, internet. All right. mv cosine theta minus, minus mv cosine theta. Okay. So the change in momentum in the y direction is 2 mv cosine theta. All right. Now, if we want to draw the vector that shows the overall change in momentum, all right, well, let's do that. So first, we need a little room. So I'm going to squish this down. All right. Now we got some room. Let's make it blue. What the heck? The last thing we're asked to do is find the vector, or draw the vector that shows the overall change in momentum. Okay, well, if we were to, this is our initial momentum vector, and this is the final momentum vector. So this is initial, this is the final. Change means final minus initial. So let's do this. So if this is PF, and then minus is really adding the negative, so we should add this guy. So if we were to add the negative of this, we could bring this one over there, so it would be going like that. But then if we're adding the negative, we add it going the opposite way, if you remember how vectors work. Hopefully you do. So this would be P initial, and so then the resultant would be this. Oh, okay, so this is going to be my overall change in momentum. And if you look at it, if we were to break these up into components, this, which is mv cosine theta, and this is mv cosine theta, that's 2 mv cosine theta. That is what this looks like. This is the size 2 mv cosine theta, and it is pointing up. So the change in momentum is upward with a magnitude of 2mv cosine theta. I just want to point out in this problem that we couldn't just deal with the velocities, the overall velocities, going diagonally. You had to break up the x and the y. And this is going to be true for all momentum problems. You need to differentiate between x direction and y direction. Okay, here's a problem that it includes a lot of different characteristics of momentum problems. So hopefully you'll see some of your homework problems in this problem. Okay, so in case you can't tell what this is by my beautiful drawing, these are two trucks. All right, so two trucks. We got truck B and truck A, and A is humming along in the x direction, B is humming along in the y direction, and they end up colliding at the intersection, and they collide inelastically, which means they stick together and they both move in a diagonal direction this way. Our job is to find the size and the direction, so meaning the angle of the final velocity. Okay, well, we cannot just add the momentum vectors. We can't add 500 times 25 plus 1,000 times 10. You cannot, come on, you cannot add, technical difficulties here. You can't just do this with the values. You can't just add the magnitudes. Okay, you cannot do that. You have to take into account that they are vectors and they are going in different directions. So let's see. So if we were to find the total momentum of the system before the collision in the x direction, okay, so same thing. We have MA VAX plus MB VBX, and I know I tacked on two subscripts. Okay, so VAX just means the velocity of A in the x direction and the velocity of B in the x direction, because these two quantities give us the total initial momentum in the x direction. Okay, so let's continue with B. So let's see. So MA. So this is 500 times 25, and actually, let's be correct here. So these are vectors, and so this is in the I direction, plus, and I'm writing all this out explicitly just because we're going over it for the first time. What is the velocity in the x direction of B? Oh, well, it's going in the y direction, so that means it's 0. Okay, so what does that mean? That means that the initial momentum in the x direction is 12,500 meters per second in the I direction. All right. Now, making a little, just slightly more room here. We're gonna have a room problem. Let's figure out what the momentum initially in the y direction would be. And once again, we would have MA VA in the y direction plus MB VB in the y direction. So A is still 500, but if you notice, A is going in the x direction, so how fast is it going in the y direction? It is not, so that's 0. And I accidentally wrote an equal sign there. All right. Plus, we have the mass of B, which is 1,000. I know. Let's get back to blue here. Come on, Internet. There we go. Okay. 1,000. Now we have the velocity of B in the y direction. I am really tempted to put 10 here until I look at my diagram. It's a good thing I drew the diagram. B is moving downward, or at least in that direction. Southerly, whatever you want to think about it. So what do you need? You need a negative sign. All right. So we could say that Py, all right, so the total momentum in the y direction is equal to negative 10,000 j hat meters per second. All right, so bottom line, if we were going to, and let's make this just, no, okay. All right, I guess we won't go there. If we were to say the total initial momentum, then we would say is 12,500 I hat plus a negative 10,000 j hat meters per second. All right, that is the initial momentum of the system right before the collision. Okay, well now we're going to use our knowledge of conservation of momentum, and so now we know what the initial momentum is. So isn't that the same as the final momentum? It is. So the final momentum is also equal to 12,500 I minus 10,000 J meters per second. Okay, so how does this help us? We need to find the final velocity, the magnitude, and the direction of it. Okay, well, I do know that my final momentum is equal to mass times the final velocity, don't I? I do. So my final momentum, so let's just put the numbers in that we know. 5,000 I, and you know what, let's forget this plus minus thing. Let's do minus 10. Oh, that just looks so bad. I apologize, but I am not, the internet is not keeping up with my pen. I have some issues here, among many. Okay, so this is J. Notice I'm not adding or subtracting 12,500 and 10,000. You can't, they're in two different directions. But, so what is my mass? Well, the mass now in the final, they're stuck together. So we have to add the masses together, and so that would be 1,000 plus 500, which would be 1,500 kilograms. Okay, so it's the mass of both of them, because in this final situation, they are both stuck together. And, so we need to find out what the final velocity would be. All right, well, we know that the final velocity is going to be in the same direction as the final momentum. And so why don't we just divide both by 1,500. All right, and since I already done the math for us, our final velocity vector is going to be 8.33I minus 6.66J meters per second. Okay, what are we going to do with this now? All right, well, if I need to find the magnitude, what am I going to do? Well, if we were to draw this out, this would look, yikes, let's use the pen. If I were to draw this out, this is going to look like 8.33, and this is going to look like 6.66. And if we were to add these vectors vectorially, I am going to get, that is going to be my resultant. So my resultant magnitude, I'm just going to use a squared plus b squared equals c squared, and ultimately that is going to get me, and I apologize for this being so messy, get me that. And if I were to put that in my calculator, I'm going to get a magnitude of 10.67 meters per second for my final velocity. My resultant is equal to my final velocity. All right. Let's shrink it just a little bit more so I have just a little bit more room. I'll shrink this guy. Okay, so I have that. How do I get my direction? Well, the direction means they just want you to find an angle. So take a look at this. If we, and you've done this probably more in the beginning of the year, but it's going to come back and it's a useful thing. What do you know about the tangent of theta? Tangent is opposite over adjacent. So that would be 6.66 divided by 8.33. And if you were to put that into your calculator, you're going to get an angle of 38.6 degrees. Now, what is that? That would be 38.6 degrees south of east, or below 38.6 degrees below the horizontal. If you drew it the way I did it and you said that was the angle, you're defining it already. All right? So, bottom line for this problem, you can't be adding the momentums when they're going in the x and the y direction. You can't add them as scalars. You could add them as vectors. So you have to find the momentum in the x direction, find the momentum in the y direction before the collision, put them together, and you have your initial momentum vector. Your initial momentum is equal to your final momentum because there were no external forces on the system. If you have to find the velocity, you know that momentum is equal to mass times velocity. So you can put the values into an equation, divide by the mass, and get the velocity vector. You can find the magnitude of a vector by using the Pythagorean theorem, as we did over here. And you can find the direction by getting the angles using tangent. And that is that. I can't do a video on momentum problems if I don't do one which includes conservation of energy along with conservation of momentum. All right. Many problems require you to use both so you have enough equations to figure out your unknowns. Now I'm going to give you a tip here. If you ever have an object that starts at a certain height and they want to find the velocity, after it has slid down or fallen or whatever, you're going to use conservation of energy. Most likely, if there's a collision, you're going to use conservation of momentum. If there is both, as the problem that you can see right here, you're going to use both. All right, so if we set up the problem, box A slides down the little hill and hits box B and sticks to it. So how fast will A and B move when they are stuck together? All right, so if we kind of go through overall what needs to be done here, we can see that the box is at a certain height, and do we need to know the velocity at the bottom? Well, if they're going to collide and we're going to use conservation of momentum, we're going to need to know the velocity of A right before it hits B. All right, so let's treat this problem. The first part of the problem is going to be a conservation of energy problem, and then the second part of the problem is going to be a conservation of momentum. So I'm going to put this in a different color here. All right, so we're going to say that this is position 1 and this is position 2 right before A were to touch B. I know that the energy at 1 is going to equal the energy at 2, simply because I'm telling you that there is no thermal energy loss due to friction. All right, so there's no energy loss due to any external factors here, so we know that energy is conserved. What kind of energy is at 1? Well, we know that A is at rest, so there's no kinetic, so it is just potential energy. So I'm going to try that one more time, and hopefully the internet gods will be happy with me. M G H, and this is MA. We'll put the little subscript in there. Okay. And that's all the kind of energy. We don't worry about elastic energy because there's no springs. And the energy at the bottom, well, if we're smart cookies, we're going to make potential energy equal to 0 or U equal to 0, however your book uses, all right? Right there, so it is just simply going to have kinetic energy. And that's the velocity at A. All right, and that's the mass of A. Well, nicely done. These are going to cancel. I am, just for simplicity, and on the AP test, they always have you use 10 instead of 9.8, so I'm going to do that. The height, as shown in the diagram, is 5 meters. This is going to be 1/2, and we need to know what VA is. So if we do the math, and I'm going to abbreviate things here, our velocity is going to end up being 10 meters per second. All right, so this is what, so our velocity, the velocity of A right before it hits B is going to be 10 meters per second. A is now going to go down the ramp, and it is going to hit B. Right before it hits B, it's moving at 10 meters per second. So just like in our one-dimensional problems, we have A and we have B, and then they stick together. And we need to find out how fast they are moving when they stick together. Okay, so, well, we want to find the momentum of the system before and after. So that is MAVA plus MBVB equals, and they are together. So we'll write it out the fancy way. And this is V prime, and we have to find V prime. Okay, so A is 1 kilogram, and it's moving at 10 meters per second. B is at rest, so that's 0. And MA plus the mass of A plus the mass of B is 4. 1 plus 3 is 4, and we need to find V prime. All right, so that gives us simply 10 equals 4 V prime. Divide by 4, divide by 4, and so V prime is going to equal 2.5 meters per second. And that is the answer to the problem. All right, so notice conservation of energy tends to give you velocity, and you need the velocity to solve a conservation of momentum problem. All right, we made it through. All right, so just want to make sure we go over some important points here. You want to draw a picture, preferably before or after. If there's more than one direction of motion, separate the x and the y momentum. You can't just add them as scalars. And that's number 3. You can't just add them as scalars. It's a really big deal. You got to use Pythagorean theorem, and you have to write them as vectors using your I hat and j hat unit vectors. If a problem has an object and it's starting at a certain height and then it's going to collide with something at the bottom, that is a sure sign that you need to use conservation of energy to get the velocity of one of the objects right before it hits the other, and then use conservation of momentum, because now you have both your known velocity vectors. I highly suggest going through these problems without listening to the video again and see if you can do them and see if you could explain each step. If you can't explain each step, I would re-watch that part of the video. It seems like a lot of work, and it is a lot of work, but physics is a lot of work, and in order to get it, it just requires time and practice. But I know you can do it. Because remember, hardworking scholars can do anything, even physics.